In this video, I'll be discussing projectile motion and give you examples of calculations. It is part of topic 2.1 in the IB Physics Syllabus, which means it's both in SL and HL course material. Please take a moment to read the success criteria for this video. Okay, before we get into projectile motion, let's just review a little bit about throwing something vertically, that is, in just one dimension. First of all, you really should always state that up is positive because we're dealing with vectors here, and we want to make sure that when we talk about our acceleration due to gravity, which is also a vector, we're very clear on its direction. So first of all, I'm going to be ignoring air resistance, and you can see my little sketch over here to the side that if I release a ball, and now this should be going straight up and straight down, but I've moved it a little bit to the side so it's easier to see. I start off with a certain speed, let's say it's 10 meters per second. A little while later, it's slowing down, so therefore my vector should be shown as a shorter arrow. Remember, it has magnitude, the size, that's the length of the arrow, and its direction, being a vector. I get to the very top, and my little wee marking here says v equals 0. Because when we get to the very top, it actually is going to stop. It's then going to change direction. And if we don't have air resistance, when it gets to the same height, it's actually going to be the exact same speed, but opposite direction. Same if we get down here to the hand. We're going to have the acceleration due to gravity is negative 9.81 meters per second squared. That is the value in our data booklet. I love my data booklet. Anyway, please don't use the value 10 for values that are given in the data booklet. It's there. The only time you really should use 10 is if you're doing multiple choice, which we don't get a calculator for, or if the question specifically states to use the value of 10. Other than that, we should use 9.81. I've got the negative down there because I've said up is positive, and the acceleration due to gravity is downwards. Now, if you think about it, it really should be a negative value. If I throw it up, that means it's going to be slowing down in a positive direction. I think if that is one thing is being negative, the other is positive, multiply them together, I should get a negative result. Then on the way down, yes, it's speeding up, but now it's in a negative direction. Again, giving me a negative result. So my acceleration for the whole time doesn't change. It's always the same. The Earth doesn't disappear, change size, or change position. So my acceleration due to gravity, which is being caused by it, is going to be the same throughout. Now, if you were in my class right now, what I would get you to do is to get a video clip of you throwing a ball so that we can see it go through the air in front of the camera. And then I would get you to go to use your Logger Pro, a software program that I highly recommend for video analysis and using graphs. If your school doesn't have it, you should ask your teacher to look into it. It is a great site license for a certain amount of money to put a legal copy on all the school computers, teachers' computers, and student computers. And it will allow you to do video analysis as well as use a lot of their different probes. I use a video analysis, especially right now when we have many students that are at home learning from there. They can do many labs with just using their computer. All right, so if you did this and you went through the video analysis section, you can also see I've got videos on that as well. You can make a distance time graph and a velocity time graph from just looking at the picture. So here are the results of my distance time graph when I threw a ball in front of my camera. Now you can see that I've got some pictures that are in dots that are in red, and that's telling me those are my x coordinates. And on a distance time graph, you see that I've got red being a straight line. So let's remind ourselves, what does a straight line on a distance time graph mean? Hopefully you thought a straight line means constant velocity. But if I look at my vertical one, so in the y direction, you'll see here that I've got a curved line. And a curved line implies that there's acceleration. So as my ball moves through the air horizontally, so left to right, it was moving at a constant speed, but vertically up and down, it was accelerating. So here are the velocity time graphs that go along with the same distance time graphs, and let's check this out. So first of all, in the x direction, horizontally, you can see that, well, it's not perfect, and if you ever use Logger Pro video analysis like this, the velocity time graphs are a little bit more difficult to get great results from, just because the way the points get calculated. But it is still here fairly constant. Likewise, on a velocity time graph, because I have a gradient that's not zero, this is going to give me a acceleration. And you can see with a negative gradient, I have a negative acceleration. Okay, so the results then show us that horizontally we were moving at a constant speed, but vertically there's acceleration. So here I am here and I throw the ball, and I'm going to throw the ball on an angle such like this. Now, if I break that apart, that means in the x direction I had this much for a component, and in the y direction I had this much as a component. Now, I've drawn a series of dots as a parabola shape, and what I'm going to do is show the vectors as their components to show you why this ends up happening. Okay, so horizontally, let's do that one first because, well, it's the easiest. We said it's a constant speed, so then this component should never change. I should be able to draw this, I'm trying to at least draw the same size arrow in each point. Now, vertically, as we said at the beginning of this video, we know that it should be getting smaller. Up here, there is no part. Here, we're ignoring air resistance, so it should be the same as this one over here, but in the opposite direction. And then again, finally, down here. If I go back, we know from our rectangle rule or parallelogram rule that the resultant vector would be the diagonal of these if I made this back into a rectangle. So there you can see the direction that my ball would actually be moving. So the green line shows you the entire velocity vector. The blue lines are showing you the vertical components, and the red line is showing you the horizontal component that doesn't change for your velocity. Now, when we do our calculations then, because we have different types of motion happening in these two directions, we can't use the same equations. Horizontally, we can use these equations v equals d over t, but vertically, because it's accelerating, we can't use that equation. We have to use the Suvat equations. And for that reason, we're going to have to keep our information very separate when we do our calculations. Now, if we have air resistance, what does that mean? It means that horizontally, we won't actually be able to continue at a constant speed. There will be a reduction in its speed. Also vertically, I'm just going to do a couple, and I need to show them that they're getting shorter. They're also not going to be moving as far in the equal amount of time. And vertically, if I start off with here, little, we know there's nothing here. This one won't even be as big as what it was before, and same with this one. I'm going to put in my resultant velocities. And what we find is instead of getting a nice parabola shape, we get something that looks more like this. And it shouldn't look symmetrical. It should look a little bit more stunted here and a little bit steeper here than it did at the beginning. And that's because it's not traveling as far in the same amount of time. So let's go through some examples here. Let's call this a thought experiment. So we don't actually have a hunter and a monkey, but it is a fairly common example. I have on the left a ball that's going to be released here. It's going to be shot out of our little cannon towards our little toy monkey, not a real monkey. And the thing is, if they're released at the same time, my monkey is going to fall down and my ball isn't actually going to go straight forward. My ball, if we are ignoring air resistance, will travel at a constant speed this way. But by the time it reaches over here, it's also starting to fall. And because those two components are independent, that means my ball will still hit the monkey each time. It's just like when you're shooting an arrow, you don't actually shoot right at the target. You have to shoot slightly above it because by the time the arrow reaches the target, it will have fallen. So let's go through a couple of calculations. Originally, they are 0.25 meters above the bench. And we need to make sure we keep our horizontal and vertical information separately. So I usually write an H and a V to help us out. And then before I put any information in, I'm going to write down the possible variables that could be in this section. Horizontally, constant speed, so V equals D over T, and vertically could be suvat. So let's take a check. So we're looking for the time it takes to fall. Now realize that the time is true for both cases, both vertically and horizontally, and that's because time is a scalar. We also know that the height is 0.25 meters. Now that is a vertical value. So because I've got this vertical value here, I need to then put it in the vertical information. Now I'm also going from the top down. So that means this value will be a negative value because I'm measuring it in the negative direction. It's falling. I know my acceleration is going to be negative 9.81 meters per second squared. And since it's being dropped, that means my initial speed is going to be 0. Anytime we're using suvat, we know that if we have 3 pieces of information, we can find the fourth. So you might be saying, well, wait, I know 4 pieces of this information. Well, actually, this is what we're trying to look for. So we really don't have the time. Right now, I'm actually going to have to look for it. So I go to my data booklet and I say, what equation in suvat has S, A, T, and U? And because U is 0, I suggest that the very first thing you do is go like this with an arrow and a 0 through it. It's going to make our calculations so much easier. So if I do some algebra here, I get 2s over a equals t. That would be a squared. Let's cheat and just put the square root there. If I put my values in, when you put the values in, don't forget that's why s had to be a negative. So the negative 0.25 will cancel out with the negative from the 9.81. We're going to get 0.23 seconds when you put that in your calculator. And so that is, when rounded, about 0.2. Don't forget, you need to write down your unrounded answer before you show the value you're looking for. You need to prove to the examiner that you actually did pick up your calculator and calculated the value. So I'm going to erase my work here and let's start on part B. Now we can actually use our value from the first part, and instead of just putting 0.2, I'm going to use my value of 0.23. It says here to calculate the horizontal distance that the ball should travel if it's to hit the monkey before it reaches the bench. So here's what I'm looking for. It also now down in this part of the question tells me that the initial velocity was 2.6 meters per second. That was nice of them, so that didn't confuse us from above. But normally it would be giving in the first part of the question, you'd have to remember that it was only relying or referring to the horizontal motion. I'm going to use my simple equation for constant speed rearranged. So now d is equal to v times t. And my calculator gives me 0.598, but looking at my values, I've got two significant figures. So I'm going to round my final answer to two significant figures as well. 0.60 has two significant figures, and that will be in meters. Now, the previous example had the ball leaving with a horizontal velocity only, so it makes it a little easier. But in this case, we've got this archer fish, and it's spinning at an angle of 70 degrees to the horizontal. So if I drew this in, here's my vector, 70 degrees to the horizontal, and that speed 3.5. That's actually the diagonal of our rectangle or parallelogram rule. Okay, so show that the initial horizontal components of the velocity for the droplet is about 1.1. So if I want to have my horizontal component, that's going to be this one right here. The name of this side compared to our angle is adjacent. So we have adjacent and hypotenuse. That means I'm going to have to use cos. So I know that cos is adjacent over hypotenuse. You can see that I've put my values in here, rearranged. I've just done v with a subscript h to show that it's the horizontal component. And I get the value of 1.2, which is in still the same ballpark as 1.1. So now on to part B, we're going to calculate the vertical distance y to the insect. In the vertical direction, we know we need to use suvat. So let me just start by writing suvat here. And we can put in some values that we know. The acceleration is going to be negative 9.81 meters per second squared. If it's just going to get up to the top, we could use the final velocity equaling to 0. We know that its initial velocity is going to be the vertical component. So if the horizontal one was cos, this one will be sine. That'll be 3.5 sine 70 degrees. And we are looking for the vertical distance. So again, we go to our suvat and we say, which equation has S, U, V, and A? So hopefully you found it. V squared equals U squared plus 2AS. And again, since V is 0, let's make our lives a lot easier and get rid of that right away. Now when I move this around, I'm going to have to get U squared to the other side. Now these two right now, they're being attached by addition. So when it goes to the other side, it's going to be negative U squared. And over here I have now 2AS. I'm going to leave S there, but 2A and S are attached by multiplication, so I'm going to be dividing it here, and I'll put my numbers in. Now, a thing to note is that is negative of u squared. That negative sign is not inside the square. So I do get a negative number on the top, and we have our negative 9.81 down on the bottom. So they will cancel out to give me an S value that is positive, which is good because we're measuring in a positive direction. So let me pick up my calculator and put these in. Don't forget to make sure your calculator is in degrees. And in this case, I get 0.55, which means 55 centimeters above the water. Does that make sense? Probably. It's in the right kind of ballpark. And that's a good thing to check to make sure you haven't given an answer like, 55 millimeters or something, or 55 kilometers if you got some values wrong. Okay, one more example. Two spheres, A and B, are simultaneously projected horizontally from the top of the tower. Well, you know what? I really need some diagrams to help me out with this. So here we go. We've got A and B. I'll do B in blue. The difference is A has a speed of 40 and blue has a speed of 20. So I really should make my arrow here of A twice as long. So what we need to look at, which statement best describes the time traveled for the spheres to reach the ground? Well, from our question with the monkey and the ball, we know that they really should take the same time to get to the bottom. The vertical component and the horizontal components don't affect each other. They're independent. So let's think about the horizontal distance they will travel. They are not going to have the same value because one is moving faster horizontally than the other. So I can get rid of this one. Let's look at our other two examples. Both spheres hit the ground at the same time, but A lands twice as far as B. Well, it is going twice as far, moving at a constant velocity. What does the other one say? B lands twice as far. Well, definitely not, because it's not moving as fast in that direction. So here is our answer. So take a moment to read the success criteria one more time. I hope after going through and giving you some examples that you can now say yes to these success criteria.